This resource is the second in a 5-part series on the normal distribution. Part 1 looks at the basics of the normal distribution. We discuss the distribution about the mean and the probability of an amount lying between integral multiples of the standard deviation. Part 2 considers the process of normalizing a value. Part 3 considers the probability a normally distributed value will lie in some range. Part 4 combines the ideas presented in Parts 2 and 3, finding percentages for examples that require normalizing the value first. Part 5 looks at how to find the variable value that define various percentile ranks in a population, which means a specified percentage of the population is less than that value for the variable. In the previous resource, we looked at the normal curve based on some population with a mean mu and a standard deviation sigma. We saw an example in which we had to find the probability a normally distributed variable fell between two values. In that example, the amounts were both integer multiples of the standard deviation. But what happens if the value is not a nice multiple of the standard deviation? To answer these questions, we must consider the standard normal curve. The standard normal curve is defined so that the mean is 0 and the standard deviation is 1. This format makes the calculation of probabilities much easier. What we need to determine is a method to transform any normally distributed population into the standard normal population. Luckily, there is just such a process, called normalizing. The formula for normalizing a value is not that complex. Suppose we have a population with a mean mu and a standard deviation sigma for some variable. If x is a variable value, then to normalize, we subtract x minus mu and divide that result by sigma. For convenience and clarity's sake, the actual variable is referred to as x, while the normalized value, the standard normal equivalent, is called z. Z measures how many standard deviations the score is above or below the mean. Let's see some examples. For example, suppose we have the kitten example from the previous resource. The average weight of a 10-week-old kitten is 25 ounces, with a standard deviation of 4 ounces. What is the z-score if a 10-week-old kitten weighs 3 pounds, 48 ounces? To find z, we have to subtract the mean and divide by the standard deviation. We have the quantity 48 minus 25 divided by 4. So a kitten weighing 48 ounces is 5.75 standard deviations above the mean. What about for a kitten that weighs 1 pound, or 16 ounces? We have the quantity 16 minus 25 divided by 4. So a kitten weighing 16 ounces has a z-score of negative 2.25. This kitten is 2.25 standard deviations below the mean. In 1999, the average height of American women in their 20s was 64.1 inches with a standard deviation of 2.75 inches. What would the z-score be for the height of former women's basketball player Margot Didek, who stood 7 foot 2 inches or 86 inches tall? We subtract Margot's height minus the mean and divide by the standard deviation. Margot was a whopping 7.9 standard deviations above the mean. How many standard deviations away from the mean is a woman legally classified as a little person, which is 4 feet 10 inches, or 58 inches tall? We subtract the height minus the mean and divide by the standard deviation. A female little person is 2.2 standard deviations below the mean.